Now, of course, he covered Amperes Law, which, as a brief recap, is sort of like the analog to Gauss's law for electrostatics. So Amperes Law is to magnetostatics, as Gauss's law is to electrostatics. What does Gauss's law mean in touchy-feely terms? Yeah, it's what's inside that counts. So Gauss's law, you take a closed surface integral of electric flux density counting the total amount of flux in coulombs that leaves that closed surface S, and that is equal to the enclosed charge, the net charge within there. Amperes Law the topology is a little bit different. Instead of a surface, you're going across a line, a closed path integral. Of magnetic field, and in electrical engineering we call magnetic field H. Something called either the auxiliary field in physics, or the field that we shall not speak of in physics. And we found that this is equal to the enclosed current. However much total current is fluxing, is traveling through this lasso of an enclosed path. So again, it's what's inside that counts. But in this case, we've got a line around a surface over which I'm counting all of the current density to give me a net current. Here I've got a surface area encapsulating a volume through which I'm integrating and counting up all of my charge. But they're quite similar to one another. There's sort of an analogy to their integral forms. And what you should have also learned is that there's a differential form to Amperes Law, right? Do you remember what that looked like? If we express Amperes Law geometrically or mathematically, we say the closed line integral of my H field around some sort of path L is equal to the surface integral of the enclosing of the path. This over here, the surface that is enclosed by the path, integral over that surface. And it doesn't matter whether it's a flat surface or if I take sort of a diaphragm, a convex diaphragm or a concave diaphragm, as long as the edge is still on this linear path, or this path defined by L, it will evaluate to the same thing. And this is, of course, my current, my total current, which is actually my J vector dotted with this surface element of integration that's always normal to the surface that I'm integrating over. This is what we define to be current in our lectures on initial lecture on current. And this is just a path integral of magnetic field. And what's interesting about this is that there's a beautiful theorem, just as the divergence theorem is a beautiful theorem in vector calculus that is purely mathematical. It is true for all vector fields. There is another vector identity that we can apply to this situation, which allows us to come up with an elegant differential form for this electromagnetic law. And that is, of course, Stokes Theorem. We basically say that, okay, Stokes Theorem says this integral is actually expressible as a surface integral, the surface enclosed by that closed path L. And I will get the same thing if I just take the curl of H and dot it with that normal surface element of integration, counting the flux of this vector quantity. Remember, curl operates on a vector and it gives you a vector. And by counting treating that as like a flux vector field and counting all the contributions through the surface, you will mathematically get the same thing as you got up there in that line integral. So this is actually equal to this. And it doesn't matter what the surface is. I can make any surface integral of this variety for any surface S equal to this integral for that variety. If that's true, then the integrands must also be the same. And it turns out that this is the differential form of Amperes Law, often called the point form. And that's just achieved by equating the integrands. The curl of H is equal to the current density in amps per meter squared. Geometrically, what does this mean? What is the curl? Well, we know it has a very long, drawn-out explanation with differential calculus, right? But geometrically, what does it mean? It means swirliness. The curl is a measure of swirliness of a field. So I have a field solution in three-dimensional space. If that field solution is just kind of spreading out, or it's constant, or it's just kind of meandering along, it is not swirly. The curl will be close to zero, or zero exactly. If, however, my field is swirling, it connects in on itself. I look over here, it's like this. I look over here, it's like this. I look over here, it swirls around. The swirliness, something is in there spinning up the field. The swirliness will not be zero in that case. And in fact, that's really what this is saying. What current does is that it essentially spins up the magnetic field around it via the right-hand law. So don't ever tell your later in life electromagnetics teachers I taught you that, but this curl is the same thing as swirliness. And we'll actually use an example of Amperes Law today when we talk about inductance. But this is sort of like the 20,000-foot view of the lecture that Professor Michaels gave. He probably worked an example or two. Did you like the solenoid? Yeah, that's a good problem. Good problem. Solenoids are important. Okay. For the next topic, we're going to talk about inductance. We now know enough to compute inductance. And this, again, has a beautiful parallel with what we've already studied in this class, right? Remember, we studied capacitance. And capacitance is equal to electric flux, which is really just a fancy word for charge, right? Has units of coulombs. You always get the feeling, you ever see that movie Back to the Future? I always get the feeling the Hollywood scriptwriter was just like, a dropout physics student who just like, we need something cool in this time-traveling DeLorean. I'm going to make a flux capacitor. That sounds cool. I remember something about flux and capacitors when I was failing my physics class before I became a screenwriter and made millions of dollars more than my classmates. All capacitors have flux. I was joking. I was giving a talk at the RFID conference. That's why I missed last week. Was out of town, and I tried to make a passionate defense for one thing scientifically that I believe that movie gets right, and that is the proper pronunciation of the prefix giga. No, giga. Giga. The dictionary says both pronunciations are appropriate. But I insist that my pronunciation is better because this comes from the Latin gigos, and every English incarnation of this word is a soft G. So giant, gigantic. You don't say, "Oh wow, that capacitor is gigantic." So this is one of my lost causes in life, is to convert more engineers to my pronunciation of the word giga. It's the culturally illiterate technical people of this world that pronounce it giga. And every once in a while, there's a smart-ass student who always says, "Professor Durgan, that's very interesting, Professor Durgin." And I have to tell them that my name actually is not at all Latin and is completely unrelated to the term gigantic, as much as you might doubt otherwise. It's like Old English or something like that, Germanic. It means dragon in like some old Scottish language or something. Completely different etymology. So anyway, we learned that capacitance was equal to electric flux and voltage. And likewise, there's another fundamental parameter relating the magnetic behavior of two pieces of metal with respect to one another. And we call it, of course, inductance. Only depends on, for the most part, material properties and the geometry between two metals. But this is equal to the magnetic flux which has units of Webers, divided by the current used to make that flux. And if we find that when we double the current, we double the flux, and vice versa. So the ratio of those two things, I got it. You threw it across the room, and you didn't think it would come over. Let's all wait while I clean up Randy's mess. Let us now resume the class. That's okay. They would much rather listen to that than this. So, okay. So this is a fundamental attribute, and let's go ahead and we know enough to calculate this, especially now that we know Amperes Law. Let me give you an example. Let's do our old friend, the coaxial cable. In this case, we'll turn it into a coaxial inductor. We'll have a current flowing down one side, or a return current on the outer sheath, and we'll see how much flux is in between them. We'll look at the ratio of the flux to the current, and we'll be able to calculate the inductance of the system. If we want to divide by the length, we could calculate the per unit length inductance of the system. And in fact, we should know enough now where we could calculate everything we need to know about a coaxial transmission line. All that stuff we took for granted that first week of class when we talked about transmission lines. Now we can compute it. In this case, it's got a nice analytical solution. In most cases, it won't have that. But you know how to set up the problems. You know how to estimate the amount of inductance, or at least set up the integrals to calculate it. Let the computer do the rest. Let it compute that. And then you can calculate what the per unit length inductance is and the per unit length capacitance is. And from thence is a spring that issues forth all of the knowledge about transmission line theory. Velocity of propagation, intrinsic impedance. So let's do that. Coaxial inductor. So what is our scenario? We've got an inner conductor of radius A. An outer conductor, and keep in mind that these, again, are sheets of metal. Inside is a dielectric epsilon sub r, mu sub r permeability. Outer conductor radius B. This is supposed to be a circle. And if this is acting as an inductive system, I'm going to have a current sent down this path and a current sent down the outer sheath that should be equal, I and I. And of course, I drew them as total I's in terms of amps. But really, that current is going to be distributed evenly around both the inner conductor, the 2 pi A circumference of the inner conductor, and the 2 pi B circumference of the outer conductor. So actually, the current density will be stronger on the inner conductor than it is on the outer conductor. That's actually an important fact in coaxial cables. And that really means that if you want a low loss cable, you almost don't have to worry about the outer conductor because the current density is very small. The loss in a coaxial cable is usually due to ohmic losses, I squared R losses. So you want your current density to be as small as possible. And you want that improves the resistive properties of the outside of the coax. This is sort of the bottleneck in your conductive path. So it's the losses of the inner conductor that give you most of your ohmic losses. Current's confined to a tighter circumference. Remember, because of the skin effect, this actually isn't going to be a volumetric flow, even if this is a solid piece of metal. It'll all be on the outside, pretty much. Likewise, this sheath of current, it will all be uniformly spread out on the outside. So that's why a lot of times you'll see really nice copper or brass or whatever used on the inner conductor, and then they just throw some cheap aluminum stuff on the outside, braided aluminum on the outer conductor, because they don't care. They just want to make that cheap. Okay. Now, we need to figure out what is the magnetic field inside this device so we can calculate the inductance. And I know from symmetry, if this is a nice long coaxial cable, of course this is going to be the z direction. Let's make a right-handed coordinate system. X, Y, is that, oh, no. That's not even right-handed. What am I doing? There we go. X, Y cross together is equal to z. So if I were to express my magnetic field vector, well, first of all, I should probably do it in the cylindrical coordinate system because this has cylindrical symmetry to it. So it's going to be a function of rho, phi, and z. But I already said that this is a very long coaxial cable. So pretty much no matter where I move in z, I'm going to see the same problem, right? So it's not going to depend on z. Now likewise, it's not going to depend on phi either. This is radially symmetric in its problem. It doesn't matter if I observe here or here or here or here. Given the same radius and the same z, I should see exactly the same field solution relative to rotation about the z-axis. And so at the end of the day, this is really just a magnetic field that's going to be a function of rho. Furthermore, if everything is symmetric, currents are uniformly spread about that inner conductor and the outer conductor, then I can also guess that not only does this depend only on rho, but this will only have a phi component. Let's see. Is that true? Yeah, by the right-hand rule, let's see. Phi, if I was observing on the x-axis, phi hat would be this direction. And if I've got a current going down in the positive z direction, that's where the magnetic field is going to swirl around by the right-hand rule. So all based on symmetry arguments, I can make this very reduced simplification for what the magnetic field should look like. It should depend on r, or rho, and it should only be in the phi hat direction. So based on that simplification, I can actually apply Amperes Law to solve for what that field should be. Normally, Amperes Law, in the most general sense, you do it the other way around. You basically say, I have field, I want to know what the enclosed current is around that field, contained by a path that swirls around that field. Kind of like Gauss's law, I've got field, I want to solve for charge. I've got field, magnetic field, I want to solve for current. But here's a case where the symmetry allows us to do the opposite. So let's take a look. Path integral of h dotted into dl vector. What does that evaluate to? Well, I've got an integral from 0 to 2 pi. My element of integration is going to be something that points around a circle. So I'm going to pick a circle of radius rho, and I got to put a d phi prime. And that element of integration is going to be in the phi hat direction, because that's what was always tangential to the path as I integrate around a circle, a phi hat. This is my dl. That's going to dot into my a priori assumed solution, the phi component of the H field. And conveniently, like most of my board examples, it all lines up, right? I got something that has a phi hat, and I'm dotting it into something that has a phi hat. Phi hat dotted into phi hat is 1, and then the rest sort of falls out. Let's see here. In fact, what I can do here, I am integrating only with respect to d phi prime, right? I'm kind of holding rho constant. So I'm just twirling around in a circle, counting all the magnetic field components as I go around. So as a result, these two things, rho and this thing that only depends on rho, can be treated as constants. I could take them outside. And all I'm left with is this integral of d phi prime from 0 to 2 pi. That's easy. That's just 2 pi. So, continuing on in my calculation on this board, I get 2 pi rho, which I factored out, and another thing that I treated as a constant, the phi component of h. So that's what that line path integral evaluates to inside the coaxial inductor. As long as I'm between the two plates where my assumptions have been valid. So that's what that integral. But we know by Amperes law that must be equal to the enclosed current. Well, we know what the enclosed current is. It's what's inside that counts. As long as rho is between A and B, radius A and radius B, the enclosed current is going to be I. If we go beyond B, what is the enclosed current? We got an I going this way, distributed around the inner conductor, and an I going the other way, distributed around the inner conductor. Total amount I, this I cancels with this I, should be 0. So there shouldn't be any magnetic field outside the coaxial inductor. This is why we love coaxial cables. They are perfect within a margin of error. They're darn near perfect at confining fields. They don't make interference for anyone else, and they don't take in interference. They're shielded cables. They're a little expensive, but they're great for carrying signals. Yeah?
Why do the p-hats or phi-hats cancel out?
Oh, so that's a dot product in that integral, right? It's something on the phi hat dotted on something on the phi hat. So I can just take phi hat dotted by phi hat and then kind of keep the amplitudes of those vectors. Dot product of two vectors should give me a scalar. Phi hat dotted into phi hat is 1. They're collinear. And then it turns into a nice scalar integral after that. I always have to be careful in these classes. I sometimes make Amperes law look a lot less elegant, and all these vector calculus relationships look a lot elegant than they really are. Because if you look at it, like in a realistic problem where you were trying to solve complicated fields and doing a path integral over an arbitrary point in space, Amperes Law is still valid, but this will never line up like this. Your path is going to have some differential element that's going to be a function of phi hat and rho hat and z hat, or whatever coordinate system that you're using, and it's going to swirl around and change around depending on what observation point you're at as you're integrating, right? And then likewise, this is not going to be some cute little solution either. It's going to have components in every direction. And you have to do the full-on dot product of all three components to get the answer. But I'm not above skipping steps and simplifying things for the class, right? We don't need to solve it. That's what computers are for. We need to know how to set these up. We don't need to know how to evaluate them. So anyway, back to this result over on this board. H sub phi as a function of rho, therefore, must be equal to I over 2 pi rho. So inside the coaxial cable, I have a phi component of H, phi component of magnetic field. It's always proportional to the current, and it falls off 1 over rho. So the further I get away from the center conductor, this marker was my center conductor. Current's going this way. Right-hand rule, I got magnetic field flux in this way. The intensity of that field, it's always going to point in the phi hat direction, but the intensity is going to fall off as I move away from the inner conductor. And it gets to be a minimum when I get to the outer conductor. Then it falls off to 0. Okay, so what has that bought us? Well, what we need to do now is calculate the total magnetic flux between the two conductors. And for that we use the your material relationship. B is equal to mu H. This is magnetic field. This is what electrical engineers call magnetic field. This is magnetic flux density. Webers per meter squared. This is units of Henrys per meter. That's permeability. And this is amps per meter. Units, these are the units I like to use. Units in magnetic field and magnetic materials gets crazy. We have Gausses, Teslas, Webers, Orsteds. Stick with Webers because they're kind of more SI compliant. That's my recommendation to the class when people measure magnetic fields. So anyway, and I will give a lecture maybe the last week of class about where mu comes from. Remember I explained in about 5 minutes where epsilon came from? It would take me about 5 months to explain all the different varieties of mu. We're going to give a crash course on magnetic material, something your book doesn't cover and something most EMAG classes don't really delve into, but I think is kind of important, especially for today's engineer, to understand the different mechanisms of magnetism, what is and what isn't possible with those materials. So we'll save that till the end of the class. But you have at least seen this constitutive relationship in your physics class, right? You have a material. If it's free space, it's mu naught, 4 pi times 10 to the negative 7th Henrys per meter. If you have a material present, you can actually get a mu slightly less than this, or slightly more than this, or in some cases many thousands of times more than that. And we use the same trick where mu is equal to mu r mu naught. So a lot of times people will express the actual permittivity in Henrys per meter as the free space permittivity times a relative unitless value. So we call this relative permeability, not permittivity. Relative permeability. And so in the problem statement, I said that there's a mu r in the dielectric, some sort of material. It's probably mu naught. It's always mu naught in this class unless I tell you otherwise. And if I say, oh yeah, it's a magnetic material. For the most part, it's going to be mu naught. But let's just leave it in as mu sub r just to say we can do that general problem. So in that case, B, in this instance, is going to be mu R times mu naught I, and of course this is my mu, collectively these two multiplied together, 2 pi over rho, and this is in the phi hat direction. That's flux density, Webers per meter squared. I need to make a flux integral over an area between the two conductors that tells me what's the total amount of flux in this scenario. So to draw my coaxial cable again, this is of course my inner A, my outer B, and let's give it a physical length because we're going to have to do a let's call this D, this dimension D. This is the magnetic flux density inside the coaxial cable. To do this integral, I'm going to set up a rectangle whose edges touch the inner and outer conductor, whose one edge is sort of parallel to the z-axis. And it doesn't really matter which orientation I put this thing in because I'm always going to get the same amount of magnetic field fluxing through it. In this case, based on the previous diagram, I've kind of aligned it so that it's in the xz plane. And therefore, phi hat kind of points in the same direction as y hat. Does everybody see that? The way I've set this up? So in order to do a flux integral, I need a surface, which in this case is my rectangle. I am going to count the flux going through that, which means I need a perpendicular surface element of integration. In this case, we said this is going to be phi hat direction, and it's got to slide around in x and y, or x and rho, actually. So let's do it this way. Let's see. I'm sliding around. Oh, no, z. We called this z. And we said this is x. Let's do it that way. X and z. That's my rectangle. Let's go ahead and do dx prime and dz prime as my elements of integration. And, of course, I can plug this directly into here. Again, the problem is conveniently lined up so that my phi hat dots into something that also has a phi hat direction. The phi hats dotted into themselves is equal to 1. And what I'm left with is a nice scalar integration over dx prime and dz prime of mu I 2 pi over rho. Now, I gotta be careful here because my rho, as I move out in x, my rho gets farther away. So let me put that as x prime. When I'm lined up in this rectangle, x prime is equal to my distance from the z-axis. So there's nothing wrong with doing that. Now I got to put the elements of my limits of integration on here. Let's say I'm going from 0 to d along this rectangle, and I'm going from a to b along x prime. Well, this is an easy integral to evaluate. From 0 to d of dz prime, nothing else depends on z. That's just d. This one's a little bit trickier, but it's not anything we haven't seen in basic calculus. We're integrating 1 over x prime with respect to x. That's, of course, the natural logarithm when you evaluate it. So my final answer, I'm evaluating it from a to b. So I get natural log b divided by a. Everything else is a constant. I picked up a d. I've got a mu. I've got an I. I've got a 2 pi. And that's it. That's my total amount of magnetic flux in units of Webers. Okay, we've done a lot of math to get to this point, but let's not forget the original definition. The total amount of flux between those two conductive paths that are carrying currents divided by the current, I, is equal to the inductance of the system. So if this is my final answer, then the inductance of the system must be equal to mu d over 2 pi log b over a. Does that dimensionally check out? Well, let's see. I've got meters over meters in a logarithm, so that's unitless over there. That's just a constant. Henries per meter, meters. I get henries. That's a unit that we all know is inductance. If I want per unit length inductance, as if I was doing a transmission line analysis, I got to divide by my length d to get henries per meter. And lo and behold, this is exactly what we gave as a formula the very first week of class for our inductive inductance on a transmission line. Mu over 2 pi log b over a. How many remember that formula from the first week of class? No one? Oh, thank you. Thank you. Thank you. It was a long time ago, I admit it. It was a long time ago. And so now, remember in class when we talked about capacitance, we worked through the example of per unit length capacitance of a coaxial cable. And what did we say that was? That was epsilon, let's see, I think it's 2 pi epsilon over the natural log b over a. We did the same kind of integrals, calculated the per unit length capacitance. And now let's see. Z naught on a transmission line, the intrinsic impedance is the square root of L over C. Does this check out? Yeah, it does. Look. We get 2 pi log b over a, the square root of mu epsilon. We can control the intrinsic impedance by controlling the dimensions of the capacitor and the stuff we fill it with, the dielectric properties that we fill it with. The velocity of propagation was 1 over the square root of LC. If I multiply that result we just got with the result we got a couple weeks ago, what do we see? Let's see. We get 1 over the square root of logs cancel because one's in the numerator, one's in the denominator. Same with the 2 pi's. All we get is mu epsilon, square root of mu epsilon in the denominator. That checks out too. We know this has units of velocity, of propagation, and it all kind of works out in the physics. So we've really come full circle in this class, right? We now understand everything there is to know, more or less, electrically about a transmission line. You can now analyze signals at high speeds to your heart's content in any crazy structure you dream up. You make a big bird-shaped coaxial cable with a cross-section of a big bird with an interconductor. You could actually put that in a computer, set up the integrals, and calculate the velocity of propagation, the intrinsic impedance, the per unit length inductance and capacitance. If for some reason you discover that that's a unique and intrinsically interesting way to transport signals, you could patent it, you could license it to Cisco or whatever. You could remember your professor that taught you that when you're doling out gifts from your private tax-deductible foundation or charity. A professor can dream, can he? Can he? Well, any questions so far? The per unit length capacitance from? So this was a lecture that we did a couple weeks ago when we covered capacitance. I did the exact same. What is the capacitance of a coaxial capacitor that was of length d? The exact same problem here. And what we came up with using the same basic field analysis was that the total capacitance was 2 pi epsilon d over the log of b over a. And to get per unit length, you just divide by the length. And that's what we came up with. Any other questions? Pretty straightforward, right? Okay. Let's talk a little bit. We're going to do a little bit of this is not quite magnetostatics. We're going to leave the world of magnetostatics and fill in the last missing component of our Maxwell's equations. So let me show you where we're at in terms of analysis. We have a set of differential equations that we've been playing around with in this class. And they look a little bit like this. We know that the divergence of the electric flux density vector is equal to the volume charge density. That's basically the Gauss's law in differential form for electric field, right? Sourciness of the electric field is equal to the presence of charge, positive or negative. We know from Amperes Law that the curl of the magnetic field vector is equal to the current density. A way to say this in word form is that magnetic field swirls around electric current. Now, there's some symmetry here. In this class especially, D field is equal to just a constant times E field, permittivity times your electric field. And of course, B field, magnetic flux density, is equal to permeability times magnetic field. So there's kind of a relationship between D and E and H and B. We haven't said anything about the sourciness of B field. So we kind of have a gap in the knowledge. If you want to make an analogy, what is a magnetic charge? We haven't talked anything about the presence of magnetic charges. But in order to kind of complete the symmetry, you see that it'd be nice if there was something in here. We had a relationship like this one for B field. And likewise, for the electrostatic field, we know that the curl of E is equal to 0. So did we ever study that? Well, that's the same way when the curl of something is 0, when there is no swirliness in the field. That means if you do one of those path integrals, you'll always get the same value that you end up with. So as long as you complete the path in an electric field. And that's true for electrostatics. That's not true when E field starts to change. So there's going to be a gap here. And there's going to be another term here that we need to talk about later. Once we fill in those terms, we will actually arrive at Maxwell's equations, the complete form. And so what we're going to start to talk about is what should go here. And now we're kind of tiptoeing into the field of electrodynamics. But once we cover inductance, it actually makes sense to talk about electrodynamics. Because there's a beautiful symmetry that we can all probably appreciate from the definitions of capacitance and inductance that we've put on the board. What is that symmetry? Well, let's take a look. In this definition of capacitance over here, I have charge is equal to capacitance times voltage. That's just a mathematical expression of taking the denominator and multiplying it by both sides of the equation. You get charge in coulombs is equal to capacitance in farads times voltage. Oh, that's nice. Well, if we wanted a time-varying situation, if charge is changing, what happens? Let's differentiate both sides of this equation with respect to time. So I get dq dt, the change in charge, coulombs per second, which we, of course, know as the unit amps. That's current flow. And that is equal to, well, normally I'd have to chain rule this thing, right? But if the physical problem isn't changing, my C is a constant. That's what we've been saying all along. Capacitance in a system is constant with respect to the geometry and the material. So I can just take this in and write dV dt. And lo and behold, I have my basic fundamental circuit relationship. I is equal to C dV dt. Change the voltage with respect to time. That'll give you current flow to and from the two pieces of metal in the capacitor. Very straightforward. Well, we always like symmetry in electromagnetics. So if I do the same thing down here, and I've got total magnetic flux. A lot of times we like to write magnetic flux as capital psi or capital phi. I'll do it as capital phi here with a sub m next to it to denote that it's magnetic flux. And that is equal to Li. I'm just taking current, multiplying both sides by current. I get magnetic flux is equal to the inductance in henries time, oh, that's L. Put it over on this side. Inductance in units of henries times current in unit of amps. And this, of course, has units of Webers. If stuff is changing in my circuit, I differentiate both sides with respect to time. Change in flux with respect to time is equal to, well, again, L is a constant. So I have L di dt. Doesn't this look familiar? What form do you know this circuit relationship as? Voltage, yeah. Your inductor relationship for an inductive element in your voltage or in your circuit analysis is voltage equals to L di dt, which implies that the change in magnetic flux is actually equal to the voltage. And that's actually what Faraday's law is.